Okay, so now we're going to take a brief foray away from energy and enthalpy to talk about properties of gases and materials in the gas phase. So let's first start off by listing some characteristics of gases. So we should first note which materials are gases, and among just the elements, among atoms in their elemental form, at room temperature, there are a few of them that are gases. So all of the noble gases in group 18. There's also hydrogen, nitrogen, oxygen, fluorine, and chlorine, all diatomic and all gases at room temperature. However, beyond that, there are no gases that are just in their elemental form at room temperature. But there are a whole host of molecular gases. So these are compounds, and specifically, they need to have low molar mass, generally less than 100 grams per mole for the molar mass. And it must be non-metals only. It can't be any ionic compounds. Ionic compounds have very high melting points, not to mention boiling points. And metals themselves tend to have much too high of boiling points to be a gas at room temperature. I can list just a few examples of common gases that have, you'll notice they all have low molar masses if you add up the atomic weights. And some of these are very familiar. Carbon dioxide, methane, propane, which is basically just gas used to generate gas stoves or sometimes for heat in homes. There's some other ones you may be familiar with here, but you'll notice just that these are just some common ones that have low molar mass for these gases. Now, we also can talk about materials in their gas phase that wouldn't normally be gas phases at room temperature. So we may talk at elevated temperature or at various non-standard pressures. And whenever we talk about the gas phase of a material that's normally a liquid or even a solid at room temperature, we refer to that as being a vapor. So we'll talk about water vapor because water itself is normally a liquid at room temperature. Now, one very important point out of when talking about gases is that the chemical properties of gases can be wildly different. Oxygen, for example, is absolutely necessary for life. We breathe it all the time. Nitrogen, very similar, but we can't survive on breathing nitrogen. It doesn't cause our bodies to work. And so the chemical properties can vary significantly, but the physical properties of gases are very similar. So chemical properties are different, physical properties are very similar. So what are some of those physical properties? Well, first, gases expand to fill whatever container you put them in. So the volume of a gas, regardless of the identity of gas, is equal to the volume of the container that it's in. So if we had 1 gram of oxygen gas, or 1 mole of oxygen gas, if we put that in a balloon, it will fill the volume of the balloon. If we put it in your living room, it will fill the volume of your living room. If we put it in an even larger building, it will fill that volume. That 1 gram or or in a separate example, that 1 mole of oxygen gas will fill the volume that it's put in. How you may wonder, how exactly does that work? Well, it comes from a couple other physical properties. First is that gases are highly compressible. So here's just an example with a piston, same amount of gas in both ones, but if we apply force onto the piston, we are able to change the volume of the gases. And this is very different from liquids or solids, which are not generally very compressible. You can take a solid and smush it as much as you can, but most things, if they're fairly dense, don't compress significantly at all. Most materials that do compress that are solids only compress because there's actually lots of air pockets in them. So if you think of like a loaf of bread, for example, a large portion of the loaf of bread is actually just air bubbles inside, and so that makes it really compressible, but it's not really the solid that's compressing. You're compressing out the air that's in there. But if you have a solid material like a table, you can push on it with lots of force, but it's very difficult to compress it. Now, this might also be a little confusing in terms of why exactly are gases compressible? Why do they fill whatever volume you put them in? Well, it comes from the fact that the molecules themselves in the gas phase are very far apart from each other. So every individual gas molecule in a gas acts as though it is completely isolated, as though it's by itself. And because of that, in any sample of gas, say we put a sample of gas in a balloon, there's a lot of empty space between the molecules, and that allows them to be compressible because you can compress and bring the gas molecules closer together because there's all that empty space. In solids or liquids, the atoms or molecules are right next to each other, and so there's not a lot of empty space, and hence not very compressible. And this also explains why the gas fills whatever material, whatever container you put it in. If the gas molecules are far apart from each other, then they just expand, they just go around and behave as if they're entirely isolated. And so then the volume, they're just going to expand because they behave all isolated, they expand to fill whatever container you put them in, expand or contract because they're compressible. Going along with this line then is just the point that because there's all that extra space between the molecules, the actual volume that's occupied by the molecules themselves is tiny compared to the volume of the container. So normally it's approximately about 0.1% of the total volume is actually occupied by the volume of the molecules themselves. And then one other thing to note with these is that gases, any mixture of more than one gas is deemed a homogeneous mixture. So air is a homogeneous mixture. Any mixture of more than one gas we treat as a homogeneous mixture. There are cases under certain circumstances where you can have non-homogeneous mixtures of gases, but for our purposes, any mixture of two or more gases is deemed a homogeneous mixture. Okay, with a little bit of that information under our belt, we need to define a couple other terms that we will use significantly whenever we talk about gases. And the first is the term pressure. We talk about gas pressure. We don't generally talk about the pressure of a liquid, but we do talk about the pressure of a gas constantly. And that's one factor we will return to a lot. So what is pressure exactly? Being force over an area. Now, what exactly is force? Well, force is defined as mass times acceleration. Now, since we're talking about gases, and most of the time we're talking about something in the atmosphere, then if we're talking about atmospheric pressure, then the acceleration we're talking about is the acceleration due to gravity pulling down on the atmosphere. And from physics, the acceleration due to gravity is given the term g, and is 9.8 meters per second squared. So atmospheric pressure itself is defined as being the gravitational force applied over a 1 meter squared area. We can think about that something like this, where we have a 1 meter squared column that runs all the way up through the atmosphere and contains the air molecules in that column, and gravity pulls down on the air molecules in that column. Now, all that mass of air, all that air in that column has a mass, approximately 10 to the 4th kilograms. And so that's the mass. And then the acceleration due to gravity, gravity is pulling down on that. So we can calculate the force due to gravity as simply being 10,000 kilograms approximately times the acceleration of 9.8 meters per second squared, and we come out with a force of 1 times 10 to the 5th kilograms meters per second squared. Now, if we take that force and divide it by the area of 1 meter squared, we'll come out with 1 times 10 to the 5th kilogram per meter second squared. And this is now then an estimation for the pressure, the atmospheric pressure. Now, we don't tend to use this unit kilogram per meter second squared. This is actually given a specific term. So this unit is known as the Pascal. It's named after Blaise Pascal, a scientist who did studies or experiments on gases. And this is the SI unit for pressure. Now, for atmospheric pressure, if we do things in terms of pascals, it generally tends to be a large number. So we will frequently convert that to kilopascals simply by dividing by 1,000. So we'll end up with, this is also 100 kilopascals. Now, if we wanted to measure the atmospheric pressure on a given day, doing this kind of estimation and calculating the mass of air in that column, particularly with changes in air density and cloud cover, that would be really complicated and probably not very accurate. And so it turns out there's a much more useful tool for actually measuring atmospheric pressure. And that's a tool that was invented by Evangelista Torricelli in the 1600s. He was an Italian scientist, and there was a lot of debate at that time about whether or not the atmosphere actually exerts a pressure on us or not, whether the atmospheric pressure, whether the atmosphere was weightless or if it had some kind of weight. And Evangelista Torricelli sort of solved this debate by inventing a tool known as the barometer. And it looks something like this. What he essentially took is a giant dish that's filled with liquid mercury metal. So mercury metal is a liquid at room temperature. And he took a tube that was closed on one end and open on the other and submersed it entirely in that bath of mercury, filled the tube entirely with mercury, and then inverted it so that the closed end of the tube was up and the open end of the tube was still below the surface level. Now, he argued, if the atmosphere has no weight, then the mercury that was in the tube should just fall completely out of the tube. It should just fall all the way down out of the tube just by gravity's force on it, and there should be nothing. It should just be an empty tube. See there. But what he observed is that that's not quite true. The mercury does fall down a little bit, so we have a little bit of an empty space, but then it stayed at a certain level in the column. And he argued this only makes sense if the atmosphere has actual mass and is being and there's a pressure that's being exerted downwards, and that pressure ends up being equal to the pressure of that column of mercury, the pressure that's exerted by gravity pulling down on that column of mercury. If the and that column of the height of that column of mercury will adjust to be equal to that atmospheric pressure. That way both things are equal. If there were no atmospheric pressure at all, this would just fall entirely down by the force of gravity. So it's only the force of the atmospheric pressure pushing down on the outer pool that keeps it at that certain height. And so the height of the mercury column is then a measure for the atmospheric pressure, and it's a location specific measure because the atmospheric pressure may vary given the height from sea level, what elevation you're at, or the particular cloud cover on a certain day. And so he noticed that the height of that mercury column would change on a day-to-day basis. And so this allows kind of a daily measure of atmospheric pressure. Now, using this method, he found that atmospheric pressure, the standard atmospheric pressure is 760 millimeters of mercury in height. So now we have a different unit for atmospheric pressure in terms of millimeters of mercury rather than pascals. So we've got these two different units, millimeters of mercury and pascals, and it turns out we actually have a large number of pressure units. So we've got atmospheres, we've got torr. Torr is actually essentially the renaming of millimeters of mercury in honor of Evangelista Torricelli. And then we've got pascals or kilopascals. There's also a unit known as the bar. How do we relate between all of these? Because we do need to be able to convert between pressure units. So here's kind of the conversion factors. 1 atmosphere is equal to 760 millimeters of mercury, and millimeters of mercury and torr are equal to each other. So that's 760 torr. That's also equal to 1.01325 times 10 to the 5th pascals, or you can divide by 1,000 to get 101.325 kilopascals. And bar is actually just 10 to the 5th pascals, so it would be 1.01325 bar. So this is kind of the conversion factor between all of these different pressure units, and will be useful to us as we go forward. Now, Evangelista Torricelli invented the barometer as a tool for measuring atmospheric pressure, but what if we wanted to measure the pressure of an individual gas? Maybe not just atmospheric pressure, maybe not the atmosphere, but just some sample of a gas. And so similar to Torricelli's barometer, people invented something known as the manometer, and it looks something like this, where you have a U-tube that's filled with mercury, or that has mercury in it, and one end of the tube is open to atmosphere, and the other end of the tube you can attach to your gas sample. And using similar process to the barometer, we are able to calculate the pressure of the gas as long as we know the pressure of the atmosphere, and we can measure the different heights of the mercury levels on both sides of the U-tube. So here's just the equation. So the pressure of the gas is equal to the atmospheric pressure plus the pressure that comes from the height difference here in H of the mercury levels. Now, to be specific, it's the height on the atmosphere side minus the height on the gas side. So shown here, the height on the atmosphere side is higher than on the gas side, but it could be the other way around as well. So let's go through a specific example of how we would calculate the pressure of a gas this way. So one day is 764.7 torr, and a sample of gas is connected to the U-tube manometer as shown above. What's the pressure of this gas in atmospheres? Okay, so we're given a couple things here. So the first thing to point out, so we've got our equation, but the first thing to point out is that we need to make sure that our units are all uniform. So we've been given the atmospheric pressure in torr, but the height here, this is in millimeters of mercury. So we just have to make sure that our units match each other. Now, turns out that 1 millimeter of mercury is equal to 1 torr. Like the millimeters of mercury and torr are equivalent. So in this case, it's all right. So what we do then is we'll calculate the difference in these heights. So we'll take the atmospheric side, 136.4 minus 103.8. That will get us the pressure and height in terms of millimeters of mercury. And we can convert 764.7 torr to millimeters of mercury very simply. And so I can first plug that information in here. So the atmospheric pressure is 764.7 millimeters of mercury, then plus the difference here in the heights. And we calculate it through and come out with the pressure of the gas being 797.3 millimeters of mercury. Now, I've been asked for this in atmospheres, though, so I have to convert from millimeters of mercury to atmospheres. So 1 atmosphere is equal to 760 millimeters of mercury, so I set that up to cancel millimeters of mercury and come out with 1.049 atmospheres for the pressure of this gas. Now, normal atmospheric pressure is about 1 atmosphere, and what we can sort of tell just by looking at this figure is we should be able to tell immediately, looking at the figure, whether the pressure of the gas is greater than the atmospheric pressure or less than the atmospheric pressure. If it's greater than the atmospheric pressure, then the gas is going to push the mercury farther down away from it, and so the height on the gas side is going to be lower than the height on the atmosphere side. If the opposite is true, if the pressure of the gas is less than the atmospheric pressure, then atmospheric pressure is going to be stronger. It's going to push the the height on the atmosphere side lower than the height on the gas side. So we should be able to identify those really quickly, and then be able to check ourselves with our final answer. Is our pressure for the gas greater than or less than normal atmospheric pressure, or than the starting atmospheric pressure? And here we can see that the pressure is greater for this gas, is greater than the atmospheric pressure.